Welcome to this lecture on the orientation of magnetic dipoles in NMR. Today, we will explore how nuclear magnetic resonance, NMR, works, focusing on the behavior of magnetic dipoles under different conditions. NMR is a fundamental technique in chemistry that allows us to analyze the structure of molecules by observing how atomic nuclei interact with an external magnetic field. The principle behind NMR is that certain nuclei, such as hydrogen and carbon-13, possess spin and act as tiny magnets. When placed in a magnetic field, these nuclear magnets align in a specific way, leading to measurable energy differences. Understanding these fundamental principles will help us comprehend how NMR spectroscopy is used in chemical and biological analysis. Let's begin with the basic concept of magnetic dipoles in the absence and presence of a magnetic field. NMR stands for nuclear magnetic resonance, and it's a non-destructive method used to determine the structure of organic compounds, study molecular interactions, and even diagnose medical conditions through magnetic resonance imaging, MRI. The technique works by detecting the magnetic properties of atomic nuclei, particularly those of hydrogen and carbon atoms. The behavior of these nuclei in a magnetic field, their energy transitions, and the interactions between them provide valuable data. This data is then interpreted to infer the atomic environment of the molecules in question. Now, let's discuss magnetic dipoles. Every nucleus has a magnetic moment due to the spin of protons and neutrons within the nucleus. These magnetic moments are called magnetic dipoles. Understanding how these dipoles behave is crucial in NMR. When a magnetic field is applied to a sample, the magnetic dipoles align themselves in the field, either parallel or antiparallel to the field direction. This alignment influences the energy states of the nuclei and forms the basis of NMR's ability to detect atomic level information. The concept of spin is fundamental to NMR. Spin refers to the intrinsic angular momentum of atomic nuclei. In the context of NMR, we focus on how the spin states of nuclei are affected by external magnetic fields. The nuclei can adopt different spin states, with each state corresponding to a different energy level. When exposed to a magnetic field, nuclei either align with or against the field, resulting in different energy levels. A pulse of radiofrequency radiation can cause the nuclei to transition between these states, and the energy released or absorbed during this transition provides the data we measure in NMR experiments. In the absence of an external magnetic field, nuclear spins are randomly oriented. This means that the tiny magnetic moments associated with each nucleus are distributed in all directions without any preferred alignment. There is no external force acting on them, leading to a completely disordered state. This randomness is significant because it implies that there is no measurable net magnetization in any direction. The nuclear spins exist in a state of equilibrium, where they do not exhibit any preference for alignment. However, when we introduce a magnetic field, the scenario changes dramatically, which brings us to the next slide. In the absence of a magnetic field, the magnetic moments of nuclei, shown as spinning particles, are randomly oriented. Without an external magnetic field to align them, these moments point in different directions, and there is no collective behavior or organization of the spins. This random distribution is the natural state of nuclei before any magnetic influence is applied, which is a key concept in understanding how NMR works when a magnetic field is introduced. When a magnetic field is applied, nuclear spins begin to align with or against the field. This results in two distinct energy states: a lower energy state where the spins align with the field, a higher energy state where the spins align against it. The distribution of nuclei between these two states is governed by Boltzmann statistics. which states that more nuclei will occupy the lower energy state than the higher energy state. This energy difference is crucial for NMR spectroscopy, as transitions between these states produce the signals we detect in an NMR experiment. The stronger the applied magnetic field, the greater the separation between these energy levels, leading to enhanced signal detection. When an external magnetic field is applied, the magnetic dipoles of the nuclei align with the field. This alignment is shown in the image where the magnetic moments of the nuclei, depicted as spinning particles, all point in the same direction as the applied magnetic field. This alignment creates a more organized arrangement compared to the random distribution in the absence of a magnetic field. The nuclei now experience a specific interaction with the field, which is fundamental for NMR processes like precession and spin flipping. This orderly arrangement is what allows scientists to manipulate and measure the behavior of nuclei in NMR experiments. In nuclear magnetic resonance, NMR, the energy difference, dE, between the alpha spin and beta spin states is a key factor in the spin flipping process. This energy difference is given by the formula delta E equals H gamma H02 pi, where H is Planck's constant, a fundamental constant of nature. Gamma is the gyromagnetic ratio, a property that is specific to each type of nucleus. H0 is the magnetic field strength, which influences the energy gap between the two spin states. The energy difference between these two states dictates how much energy is required for a nucleus to transition from the lower energy alpha spin state to the higher energy beta spin state. This energy is supplied by radio frequency pulse, which matches the resonance frequency of the nucleus and induces the spin flip. Once the nucleus absorbs the energy, it flips from the alpha spin state to the beta spin state. This change in spin state is what allows NMR to generate detectable signals. These signals are then analyzed to determine key information about the sample, such as its molecular structure and chemical environment. Precession refers to the motion of a spinning nucleus around the axis of the applied magnetic field. Instead of aligning perfectly, the nucleus traces a circular path, much like a spinning top wobbling around its axis. This precessional motion occurs at a specific frequency known as the Larmor frequency, which is determined by the type of nucleus and the strength of the magnetic field. Understanding precession is important because it forms the basis of how we detect NMR signals. When an external radio frequency pulse is applied at the Larmor frequency, it can excite the nucleus to a higher energy state, which then relaxes and emits detectable signals. This concept is key to obtaining meaningful data from NMR spectroscopy. When a magnetic field is applied, the nucleus behaves like a spinning top. The magnetic moment of the nucleus precesses, rotates around the direction of the magnetic field. The N and S poles of the nucleus move around the field direction as shown in the diagram. Now, let's discuss the concept of precessional frequency in nuclear magnetic resonance, NMR. When a nucleus with a magnetic moment, MUB, is placed in an external magnetic field, H0, it experiences a torque that causes it to precess around the axis of the applied field. This precessional motion occurs at a specific frequency, known as the Larmor frequency, which is given by the equation N del MBH0 over H, where MB is the magnetic moment of the nucleus, H0 is the strength of the applied magnetic field, H is Planck's constant. This equation shows that the precessional frequency, Nu, is directly proportional to the strength of the magnetic field, H0. This means that as we increase the external field, the nuclei precess faster. Understanding this relationship is essential in NMR spectroscopy because it determines the resonance condition. When we apply an external radio frequency that matches this precessional frequency, the nucleus absorbs energy and transitions between spin states, generating the NMR signal. In NMR, the precessional frequency, Nu, is the frequency at which the magnetic moment of a nucleus precesses around the applied magnetic field. This frequency is determined by the following equation: Nu equals mu b h0 over h, where mu b is the magnetic moment of the nucleus, which is a measure of the strength and orientation of the nucleus magnetic field. H0 is the magnetic field strength applied to the sample. A stronger magnetic field leads to a higher precessional frequency. H is Planck's constant, which links the energy of the nucleus to the frequency of its precession. The precessional frequency is essential in NMR because it governs how the magnetic moment of the nucleus behaves in the presence of an external magnetic field. When placed in a magnetic field, the nucleus magnetic moment doesn't simply align with the field. Instead, it precesses, or rotates, around the field axis at this specific frequency. The frequency at which this precession occurs depends on the magnetic field strength and the intrinsic properties of the nucleus. By applying the right radio frequency RF pulse tuned to the precessional frequency, we can manipulate the spins of the nuclei and gain valuable information about their environment, such as chemical shifts, molecular structure, and interactions. The magnetogiric ratio is a fundamental property of a nucleus that determines how strongly it interacts with a magnetic field. It is a constant for each type of nucleus and dictates the Larmor frequency, which governs precession in NMR. For example, the magnetogiric ratio for hydrogen 1 is significantly larger than that of carbon 13. This means that, under the same magnetic field, 1H will precess at a much higher frequency than 13C. This property is exploited in NMR spectroscopy to selectively analyze different elements in a compound. The Larmor frequency is the frequency at which nuclear spins precess in an external magnetic field. It is given by the equation, where gamma is the magnetogiric ratio and B is the magnetic field strength. This relationship shows that the precessional frequency increases with increasing magnetic field strength. By adjusting the applied magnetic field, we can selectively excite specific nuclei within a sample, allowing us to analyze complex molecular structures. The resonance condition in NMR occurs when the energy of an applied radio frequency pulse matches the energy gap between the two spin states. This allows the nucleus to absorb energy and transition from the lower energy, alpha spin state, to the higher energy, beta spin state. Resonance is crucial because it enables us to manipulate nuclear spins and generate NMR signals. The specific frequency at which resonance occurs is determined by the nucleus's magnetogiric ratio and the strength of the magnetic field.
In nuclear magnetic resonance, NMR, spin flipping refers to the process where atomic nuclei absorb energy at their resonance frequency. This frequency is typically provided by a radio frequency RF pulse. When the nucleus absorbs the RF energy, it undergoes a transition from a lower energy alpha spin state to a higher energy beta spin state. Alpha spin state, the nucleus aligns with the external magnetic field, representing a lower energy configuration. Beta spin state, the nucleus aligns opposite to the magnetic field, which corresponds to a higher energy state. This spin flipping process is fundamental in NMR because it generates signals that we can detect and analyze. By studying these signals, we can gain insights into the chemical environment of the nucleus and ultimately, the molecular structure of the substance being examined.
The image illustrates the spin flip process, where a nucleus absorbs energy from a magnetic field, H0, and transitions from the ground state to the excited state. In nuclear magnetic resonance, NMR, the orientation of magnetic dipoles in an applied magnetic field is a crucial concept for understanding how NMR works. The way these magnetic moments align or interact with the field affects the resulting signals and spectra, which are key to obtaining molecular information. Furthermore, the ability to manipulate and measure these interactions through processes like spin flipping and precessional frequency provides invaluable insights into the molecular structure, dynamics, and chemical environments of the substances being studied. NMR is a powerful tool that leverages these principles to help scientists and chemists understand the fundamental nature of matter. Thanks for watching. We appreciate you taking the time to learn about NMR and its key concepts. If you have any more questions or would like to dive deeper into any part of this topic, feel free to reach out.